Afterword End of an ERA, Conclusions and Lessons Learned. The 6-year endeavor progressed from innovative ideas to multiple designs, analytical models, wind tunnel tests, ground-based experiments, and testing of actual flight hardware in a relevant environment. ERA project teams employed an incremental process to achieve their ambitious goals in an orderly and logical fashion. Throughout Phase 1, researchers strove to determine whether certain technologies were, in fact, viable. Lessons learned from more than 30 of these smaller experiments paved the way for selection of the 8 integrated technology demonstrations undertaken during Phase 2. The ERA project was organized so as to mature the most promising technologies and advance aircraft configurations to meet midterm goals for community noise, reduced fuel burn, and NOx emissions. Researchers were also tasked with determining the potential impact of introducing these advances into the next-gen air transportation system. The solutions they have achieved will undoubtedly reduce fuel consumption by up to several percentage points for the aviation community. That may not sound like much, but shaving aircraft fuel consumption by even a few percentage points will save millions of dollars and help protect the environment from harmful emissions. Work within the ERA project was coordinated with research performed by other programs within NASA's Aeronautics Research Mission Directorate as well as other federal government agencies. NASA also put mechanisms in place to engage academia and industry, including working groups and technical interchange meetings, and Space Act agreements for cooperative partnerships. In addition, the NASA research announcement process provided for full and open competition for the best and most promising ideas. With the exception of proprietary data, the ERA project disseminated all research results to the widest practical extent. Most of the technologies we looked at, like low-noise landing gear or adaptive trailing edges or engine technologies, are broadly applicable to a number of different aircraft configurations, said Rich Walls. Throughout the 6-year span of ERA, we were looking at trade-offs between better technologies and different aircraft configurations. 3 of these new technologies and concepts may soon start appearing on produced tie-in airplanes. In 2016, FlexSys formed a joint venture with Aviation Partners Incorporated, of Seattle, Washington, to commercialize the wing morphing technology. Additionally, NASA and Air Force researchers have begun a second phase of OC testing at AFRC. Future efforts in the FAA Clean program may advance Perseus into TRL-6 and TRL-7. Advanced turbofan and combustor technologies evaluated during the ERA project are also moving forward. Although most ERA technologies were not intended to be configuration-specific, a great deal of effort focused on development of the HWB concept. This revolutionary configuration was the first modern commercial transport designed to completely move away from the traditional tube and wing paradigm. You take an airplane from, say, 1950, and an airplane from today, and lay them on top of each other, and they have almost exactly the same outline, said Kevin James, ERA project manager at ARC. He added that in order to realize dramatic improvements in fuel economy, emissions, and acoustics, we have to keep looking and sometimes think outside the box. With a hybrid wing body, depending on how you control the wake and how you put the engines on it, we have significant improvements in fuel burn and also improvements in noise. Testing of the X-48B and X-48C successfully demonstrated HWB low-speed flight control characteristics. Controllability and construction methods for building a flat-sided pressure vessel were only 2 of the key enablers for designing a practical HWB. Engine operability was another. Wind tunnel testing at LaRC helped researchers determine how to integrate modern engines with the HWB airframe. Work by various manufacturers on BWB and HWB configurations continues. 5 By the time the ERA project concluded on January 7, 2016, NASA had invested more than $400 million, with a further $250 million of in-kind resources contributed by industry partners. The cost may have been worth it, according to Dr. Haiwan Shen. If these technologies start finding their way into the airline fleet, our computer models show the economic impact could amount to more than $255 billion in operational savings between 2025 and 2050. 6. The mandate was a 50% reduction in fuel burn and a 42 dB reduction in noise in a cumulative fashion from a 1,999 target airplane, and where we ended up was really, really close, said Kevin James. When we start talking about numbers, even if it's cumulative, that is a huge improvement. It really is in terms of quality of life, especially for people living around airports. He took the opportunity to articulate that, among so much else, the ERA Project Act had involved a lot of hard work. There have been some frustrations, but that's kind of what makes the job fun sometimes, when you are solving the challenges. He said that he enjoyed seeing all the pieces come together in terms of project management, vehicle concepts, and systems integration. At the end of the program, it was just incredible seeing the progress that was made and the deliverables that we're getting from all the components, he said. As they come together, we're going to be in a position to say that this works, and that this is where we should be headed. 7.